So, when we talk about Markovnikov versus anti-Markovnikov, let's say we have these two asymmetric dienes, and we're only going to consider the 1, 2, 3, 4 being numbered this way. This will be analogous if you watch my previous video where I talk about what happens with asymmetric. You end up getting 2 thermodynamic, 2 kinetics. It's going to be the same. We're just going to focus on this one numbering direction for now. So, talked about a previous video. If you just add HX and we ignore, we don't have a diene, we just have a simple alkene, we should get Markovnikov addition, which means that we're going to add X to the most substituted carbon. So far so good, you should know this. And if I do light, so I do it through the free radical mechanism, I end up generating the opposite. I get the anti-Markovnikov products. How does this change when we have a diene? Well, to do this, we need to look at the mechanism. And so the way we write out the mechanism for this reaction is that actually X here is going to attack first, hydrogen gets attacked next. Hydrogen attacks next. So when we get attacked by X, we end up generating a free radical, and this is going to act a lot like a carbocation. If it's adjacent to the double bond, it's going to stabilize, be resonance stabilized. So X here, as the first start of the mechanism, is going to attack the number 1 carbon and give us a radical that is stabilized by the double bond. And the same thing is true here. So here we put both put the radicals on the bond carbon that is adjacent to the double bond, regardless of whether or not it's secondary or tertiary. So I don't have to worry about the tertiary versus secondary. Well, the reason here is that resonance always beats that out. So yes, you could have the X attacking the second carbon and giving you a free radical on the number 1 carbon, but that doesn't matter. So just a tertiary radical, it's not nearly as stable as a secondary radical that is adjacent to a double bond, which is resonance stabilized. So when we put these lambdas in here, when we start going for a free radical mechanism, the only thing we're going to change is that instead of adding hydrogen to the 1 position, we're going to add X to the 1 position. So it's an anti-Markovnikov in the sense that we're flipping the 1, 2, 1, 4, instead of being H being 1 and X being 2, now it's X being 1 and H being 2 or 4. That's all we're flipping. Now, exceptions to this. Sodium borohydride mechanism, or hydroboration oxidation, the B2H6 mechanism, that definitely is going to add like you normally would, and you would just have to consider adding the double bond separately. It's more complicated, we're not going to worry about that. But we are going to consider here that if we do something that we would expect to flip the mechanism, switching it from Markovnikov to anti-Markovnikov, particularly if it's one where there's not a lot of stereochemistry associated with the reaction. So again, go back and watch the videos on sodium borohydride, or not sodium borohydride, the B2H3, the hydroboration oxidation. Those are different, we're not going to worry about those, but definitely the free radical mechanism just switches the 1, 2, and the 1, 4 from the H and the X to the X and the H. Now, how does it get simpler? We'll talk about that in the next video.